In today's lesson, we're going to start looking at some properties, algebraic properties of limits. So starting out, the sum and difference rule is just saying if you have a limit involving addition or subtraction, we can break this up and look at it as the limit as x approaches 2 of the first term plus the limit as x approaches 2 of the second term minus the limit as x approaches 2 of the last term. So just a property, in this example, it's really not necessary to do that, but it's just showing that we can do that. We can break limits up with the addition and subtraction. And then we can also do that with products and quotients. So here we have a product of these two functions. We can break it up into two limits. The limit as x approaches 1/2 of 3x squared times the limit as x approaches 1/2 of 2x minus 1. So in some cases, it is helpful to look at limits, breaking them apart and looking at individual terms. Okay, the next property is called the constant multiple rule. And that is if you're taking the limit of a function that has a constant, like a leading coefficient out in front, we can scoot that out in front. So I could also say that it's the constant k times the limit as x approaches c of f of x. So just a basic example, if I have the limit as x approaches 4 of 3x squared, I can rewrite this with that coefficient out in front. So I could write it as 3 times the limit as x approaches 4 of x squared. Okay, so now we're going to look at limits of composite functions. So these can be simple and these can get crazy and confusing. We're going to keep things fairly simple. But what does a composite function mean? So if you think back to pre-calc, that is like f of g of x. That's a composite function. You have like this function inside a function. And notice here, we have two different functions. So we have h of x and g of x. So two different graphs. So we're looking at the limit as x approaches 1 of a composite function h of g of x. So when we're doing this, we have to look at one function at a time. So let's think about that inner function. So I'm going to think about it as just x, or the limit as x approaches 1 of the inner function. So what is that? Of g of x. So let's go to the g of x graph, and we're approaching 1. So from the left and from the right, they're both approaching 3. So now this 3 becomes the approaching part of your limit for the other function. So now it's the limit as x approaches 3 of the outer function h of x. So let's go to the h function. We're approaching 3. So approaching from the left, from the right, it is approaching 1. So that is your final answer to the original question. Okay, let's do another example. So now we're approaching -3, and it's g of h of x. So let's think about that inside function first. The limit as x approaches -3 of h of x. All right, -3, what is it approaching? Okay, they're both approaching 1. Now, this is a special case, and we'll talk about this in class some more. Because they're both approaching from above. So notice like over here, like 1 was below and 1 was above. These are both approaching from above. So they're both approaching 1, but we're going to make a little note to ourselves. It's 1 from the right because they're both approaching above. So the next limit becomes a one-sided limit. The limit as x approaches 1 from the right of that outer function g of x. So now let's go to g of x, and we're going to go to 1, but only from the right. And in this case, from the right and from the left actually ends up being the same spot, but we end up right here. So we'll talk more about these kind of special case composite functions in class. Okay, so now instead of looking at a specific function, we have a table that is showing us different limit values of the function f. And then we have to use the properties to find this. So I can use that sum difference property, and I could start by just breaking these all apart. So the limit as x approaches 4 of f of negative x plus the limit as x approaches 4 of f of x divided by 2 plus the limit as x approaches 4 of f of x over 2. Now, one thing I want you to look at is what's going on with each of these functions. Is something happening on the inside of the function or the outside of the function? If it's happening on the outside of the function, it's easy to deal with. Inside of the function is going to change. What it's going to change is what you're approaching on your limit. So I want you to think about if you plug in 4 into the inner function, that becomes negative 4. So what it does is it's changing what you're approaching. The limit as x approaches negative 4 of f of x. Now this divided by 2 outside of the function, that's the same as like a 1/2. So we could write plus, this is that constant multiple, 1/2 times the limit as x approaches 4 of f of x. So I didn't change what I was approaching on this one. And then here, because I'm changing something on the inside, that's going to change what I'm approaching. So if you think about plugging in 4 divided by 2 is 2. So that's the limit as x approaches 2 of f of x. So now we have to use our table to figure all this out. So approaching negative 4 is 5. So this whole thing is 5. Okay, approaching 4 is this. So plus 1/2 times 4. And then approaching 2 is this, plus 6. So I've got 13 for the final answer. These can be pretty confusing at first, but after you do a few examples, I think you will catch on. Okay, now our final example is using a piecewise function. So first, I want to show you a graph of this piecewise function so you kind of remember what this even means. But the idea is to be able to answer these without the graph. So here I put this piecewise function into Desmos. So we've got the first function, which is this red one, but we only care about it with this restricted domain. And then we've got the second function here, but we only care about it from -1 to e. And then the third function, so a piecewise function, it's just taking functions and restricting their domains. And then the idea is all of these together is now its separate function. So all of them together is this g of x. All right, so now I don't want to use the graph to answer these. Let's do the limit as x approaches -1. So for a limit to exist at -1, that means as x approaches -1 from the left, and as x approaches -1 from the right, they have to be equal. So -1 from the left, from the right. But if we don't have a graph, let's think about this. This is from the left. This function is from the right. And notice how -1 is part of that restricted domain. So if we are just plug in -1 into both of these, so the square root of 10 minus -1 squared, we're looking to see, does that equal 26 minus 5 times -1 squared over 7? And in this case, when you plug them in, they both equal 3, showing that the left and the right are the same. So this does exist, and it is 3. Okay, so now B is asking you the limit as x approaches e from the right. So notice how these both have e, but now this is right and this is left. From the right, from the left. So from the right is this function. So we're just plugging in e into that last function. So ln of e to the third. Property of logarithms, you can bring the power down in front, e times ln of e, and that equals 1, and 3 times 1 is 3. And now the last example. So what is the limit as you approach e? Well, if you look back at the graph, you can see that from the left and from the right, there's that jump. They're not approaching the same value. So this will be does not exist. And then if you don't have the graph, all you're doing is you are showing that 26 minus 5 times e squared over 7 does not equal ln of e to the third. So because the left does not equal the right, the limit does not exist. So there's your full video on some algebraic properties of limits.